Okay, should I start? Yeah. Okay, so first I'd like to thank the organizers for inviting me to give a talk at this very nice workshop and a chance to come to India. I'm going to talk about something that David mentioned briefly yesterday, which is basically applying the bootstrap to theories with 4 supercharges. And the reason for saying 4 supercharges I'll explain later, but it's basically because I'm not going to be in a specific dimension, so I can't use a certain n, but rather I can what's going to be fixed is the number of supercharges. And I want to mention this work is done in collaboration with some pretty amazing collaborators, Nikolai Bobev, who's now in Leuven, Valery Maschak, who's a PhD student, a PI, and who really did some amazing work here, and Miguel Paulos. So let me start. There have already been several Conformal Bootstrap talks, and so I'm going to repeat a little bit. I'm going to use the opportunity the fact that I have to repeat, I'm going to allow myself to go a little quickly, but I think it's not bad to hear this stuff again. And since I'm apparently very constrained for time, I will go fast, and I can apparently speak very quickly. So as David mentioned yesterday, conformal symmetry as sort of Bootstrap has seen a revival in the last few years. And I think the reason is basically because conformal symmetry is a very powerful tool, and it turns out to be constraining even in dimensions greater than 2, something we might not have expected a few years ago. And for me, what's very nice about it is that this tool is really non-perturbative. So it really is a sort of window into non-perturbative physics that's quite distinct from the standard windows we normally have, like supersymmetry or large N or weak coupling, because it's really something that applies in some sense that theories that are slightly less trivially constrained. And we know this, of course, that this idea and this program can be very successful in 2 dimensions where we have a little bit more symmetry, or a lot more symmetry. It turns out that it actually allows us to completely solve certain classes of theories. And it's probably a lot to hope to do something similar in dimensions greater than 2, but I have to say that in the last few years we've come much further than I think we had any right to hope we would, so who knows. So this is my usual bootstrap spiel, but in this case I'm going to add to it that I'm also going to now, even though I said sort of we don't need supersymmetry, it actually turns out to be quite nice to add supersymmetry, because supersymmetry provides different non-perturbative constraints on the theory. And when you combine these 2, they actually end up complementing each other very nicely. So SUSY constrains parts of the theory, and you can put this into the bootstrap, and then use the bootstrap to constrain other parts of the theory that aren't usually protected by supersymmetry. And that's going to be the philosophy and the approach we take here. And just to preview the results briefly, so what we get is we find universal bounds on the dimensions of certain unprotected operators in theories with 4 supercharges in D between 2 and 4. And here I mean this is between as in a continuous sense. So we're really going to be thinking about fractional dimensional theories and sort of somewhat analogous to the epsilon expansion in field theory. In particular, in every one of these dimensions, we're going to find several kinks, similar to the things that David showed yesterday. In fact, David showed you our 3-dimensional plot, so we're going to find similar plots in different dimensions. And in each of these dimensions, we're going to find essentially 1 known theory and 2 unknown theories. And we think they're related to each other across the dimensions. And then we're going to focus a little bit on 3 dimensions and do what I call precision spectroscopy or spectrometry, which is say we're going to compute the spectrum to some degree of the n equals 2 analog of the Ising model in 3 dimensions. And I'm also going to tell you that it turns out this theory is physically relevant, which is quite nice. So I'm going to quickly go through the bootstrap. I'm going to first discuss it in a non-supersymmetric setting since it's a little simpler, and then I'll tell you some of the differences we need to make supersymmetry work. So you've heard a lot of this before, but again, I think repetition doesn't hurt. So my perspective on a conformal field theory is that I'm going to define the theory in terms of its spectrum, which is a set of primary operators given by their dimensions and spins, and then the OP coefficients, which is to find some algebra on these primary operators. And the nice thing about this set of data is that even if it's an infinite set of data, it's smaller than the normal set of data we need in a field theory, and it completely defines the set of local observables in a conformal field theory. It's possible that there are non-local observables that is not fixed by this data, but the local observables are. And we all know this, but just to review, it's quite straightforward. The 2-point functions are fixed simply by the dimensions of the primary operators. And the 3-point functions are fixed in terms of these OP coefficients, and there's some functional dependence I haven't written, but the dynamical part essentially depends only on these OP coefficients. And then any higher point function you compute using the OP. So you just take successive OP contractions, combine everything into one big sum, and what appears in this sum is sort of derivatives acting on a 2-point function. This part is completely kinematical. It's fixed by conformal symmetry, and you repackage it into something you've seen many times today, which is called a conformal block, and it depends only on these 2 invariant cross ratios, which I won't write, but they're invariant cross ratios of these 4 coordinates. So this is sort of the basic building block of everything we do in the bootstrap, and in particular what we then go on and do is we impose that this algebra is, the associativity of this algebra is imposed on this correlation function. So in particular it means that I could in principle take these contractions in different orders and I want it to give me the same answer. And when you do something like this, it seems difficult at first, but I'm going to tell you practically how we do this. So it turns out that up until quite recently, we were always restricting ourselves to identical scalars. David mentioned that there are some works now which don't do that, which is very nice. But the simpler case, we simply consider 4 identical scalars. And then we say, let's try to ask if this 4-point function of these scalars is crossing symmetric with certain assumptions made on the spectrum. And I'll make these assumptions more precise in a second. But for now, we just assume that our set of possible operators is drawn from some spectrum, which I label S. And so crossing symmetry can then be phrased as taking a sum on both sides of the set of all possible operators from the spectrum. You have these conformal blocks which differ, even though I have the same operator here, because I take the contractions in different orders, the conformal blocks differ slightly in some way. What is very important is because I've taken 4 identical operators, the coefficients that appear on the 2 sides don't differ. They're the same, and they're actually squares of real numbers. And these numbers are real because I'm assuming the theory is unitary. So in a unitary theory, there's some basis of operators that makes these OP coefficients real. And so this is the building block. And then because these things are positive, you can kind of convince yourself to rewrite it in this nice way where I take everything to the left-hand side. I now have a sum of with some positive coefficients here, multiplying some functions whose form doesn't really matter, but it's fixed by symmetry. And it depends only on the dimension and spin of the operator. And it's independent of say, any other data of the theory. And then the approach you take is you basically say, it's important, it's essential that these are positive numbers. The approach you take is you say, let me consider the space of linear functionals or linear operators on this function. In particular, I'm going to restrict myself to thinking of differential operators, but you could think of a larger space of linear functions on this space. So I ask about the space, it's a linear space of derivatives acting on these functions. And this space has some nice properties. So I consider a set of linear functionals that satisfy the property that for every operator in the spectrum, they are going to be positive semi-definite. And it turns out you also want to impose some sort of normalization condition. This is not really so relevant now. But essentially, you ask for this subset of Rn corresponding to these linear functions that satisfy this condition. And since this is a set of convex conditions, the subspace you get is actually a convex subspace. And you can convince yourself by looking at this a little bit that if this subspace is non-empty, if I can find an alpha satisfying this condition for all the operators in my spectrum, then it's impossible to satisfy this crossing relation. Simply because I can take this alpha and act on this relation, and then alpha acting on these f's is always positive, and these numbers are always positive, so it's impossible to sum up to 0. Of course, if I allow these to actually, if alpha is trivial and this is 0, that's not the case. That's why you need to impose a normalization condition, that at least one of these s has to be positive. So this is the general approach we take. And an essential feature here, which is what made the bootstrap possible, is that this approach depends only on the operator spectrum. So this set MS, defined by these functionals, depends only on the data of the spectrum of the theory, not at all on the OP coefficients. So the real insight in this old Rattasi, Richkoff, Vicky, Tony paper was that they found a way to decouple the spectrum and the OPE when you ask about conformal crossing symmetry. And of course, moreover, it's nice that this is some linear optimization problem, and there are some very efficient numerical techniques that we've built on in the whole Bootstrap enterprise to solve such problems. Okay, so I told you before that I'm going to tell you, before I describe the spectrum as some abstract thing, now I'd like to just show you quickly pictorially what we usually do in terms of a spectrum. So because I wanted these coefficients to be real, I restricted myself to the space of unitary theories, and that also means that I should restrict the dimensions of operators to satisfy unitarity, and this imposes lower bounds on the dimensions depending on the spin, so they're just given here. And so in terms of these bounds, so I impose these bounds on the spectrum, of course, but beyond that, I don't want to impose very much. I want to be very general. So I allow myself essentially to have any operator. So here, I plot pictorially the spectrum. This is a spin on one axis and the dimension in the other axis. And basically, these blue is anything I allow on the spectrum. And just because of Bose symmetry, because these are identical bosons, it turns out you can only have spin 2 field. You can only have even dimensional fields in appearing this correlation function. Even spin field, sorry, yeah, putting this correlation function. So I allow a very general spectrum satisfying these bounds. The only additional constraint I impose is I assume there's some lightest scalar, which is simply the scalar appearing in this 4-point function, and then there's some gap to the next scalar, and I parameterize this gap by the dimension of the scalar, which I call epsilon. This is sort of, there are historical reasons for this. So this is the only assumption I want to make on the spectrum, and with these assumptions, I want to ask if it's possible to satisfy crossing symmetry. So I want to look at the 4-point function of this lowest dimension operator, and assume its OP has a form 1 plus epsilon plus anything, and where there's there's no operators between 1 and epsilon, and ask if this is consistent with crossing symmetry for this 4-point function. And if I do that, it turns out the answer is interesting. You can make this plot, which encodes the answer. And in this plot, basically, you have along the horizontal axis the dimension of this scalar in the external, in the correlation function. And epsilon here is the dimension of the first operator in its OPE, the first scalar operator. And so in this plot, the nice thing, the region which is white is the region in which we can make a rigorous statement that there are no solutions to crossing symmetry. We can prove this rigorously using the approach above, basically, simply by finding an alpha in the slide above. In the blue region, we can't make very strong statements. In principle, there can be many solutions that we have just not been able to rule out. But what is very nice is that along the boundary, when you cross over from the blue to the white region, you go through something kind of interesting, and actually the solutions sort of compress, and along the boundary there's generically a unique solution. And this is an essential feature in the way we use the bootstrap now, and it's quite nice. So really, if a theory happens to lie along the boundary, we can read off, it's not just that we know that it saturates some bound, but we actually can read off large parts of the spectrum and OP coefficients of this theory. This talk, of course, is not about the non-supersymmetric Ising model, but just because these plots are very common, just point out, interesting theories tend to saturate these bounds. So for example, the Ising model lives on this bound, it also lives on some kink. So this is part of the reason why this program has been quite successful. So this is just basically a review of the non-supersymmetric bootstrap, and I'd like to tell you a little bit what we do to change things when we want to do in a supersymmetric context. And we're going to focus on what is in some sense minimal supersymmetry. It's minimal supersymmetry in 4 dimensions, and its reduction to lower dimensions, which becomes less minimal. So in 3 dimensions, we're consider n equals 2 supersymmetry. In 2 dimensions, it's 2, 2. So in all cases, we're always considering 4 supercharged theories. And in fact, we're going to want to try to think of this as some sort of continuum in dimension. So we want to think of 4 supercharged theories in dimensions between 2 and 4. You'll see why this is an interesting thing to do in a second. But I want to also highlight that we like to take this dimension-independent point of view because it turns out there are many shared features across the dimensions. So you can sort of get a lot of mileage out of one common treatment. But there's an immediate problem when you do this, is that supersymmetry, in particular superconformal symmetry, is not so straightforward in arbitrary dimension, especially in fractional dimension. So one of the things we had to do to make this work is define what we meant by superconformal symmetry in any dimension between 2 and 4. And of course, to make any sense of this, you first have to restrict yourself to scalar quantities because you don't know how to work with an index in fractional dimension. But since we restrict ourselves to scalar quantities, we can proceed relatively formally. We define some algebra, which is just sort of the natural thing you would try to write down. And you want 4 supercharges and 4 superconformal charges. So we just set up the right index structure. We're quite general about what representations we allow things to be in. And it turns out that when you want to work formally, it's important to keep. So we sort of let a set of indices run from 1 to d, and d can be some number we don't specify. But it also turns out to be important to keep the transverse rotation. So I didn't specify what this algebra is in detail, but you might realize that these MIJs, for example, are just rotations. And it turns out to be useful to keep these transverse rotations around, even though they're actually not realized physically in dimensions 3 or 4. They're only realized physically in 2 dimensions. But basically what we do is you set up this algebra, and then you impose the super Jacobi identities, and that actually fixes the algebra. And you build the algebra by imposing that it's consistent with super Jacobi identities. And this fixes the algebra at the level of traces. And really, because we're working in fractional dimension, we really have to restrict ourselves to traces. And as I said, it's kind of important to keep these guys around. And then, of course, you check that these algebras give you the right thing when you restrict to 2 and 3 dimensions. They just give you the n equals 2 algebra or the n equals 2 algebra in 2 dimensions. So once you have this algebra around, you can use it to try to find the next thing you need, which is the conformal blocks. And I might, if I have time, I'll say a little bit more about this. But for now, let me just say that what we do is we look at the superconformal Casimir, which is coming from this algebra. And the conformal blocks basically have to be eigenfunctions of the superconformal Casimir. And so we act on the conformal blocks with this, and we relate the superconformal Casimir to the normal conformal Casimir. So we then find a relationship between normal conformal blocks and superconformal blocks, and we can solve that relationship in arbitrary dimension. So although, of course, we don't know conformal blocks in non-even dimensions, we do know we can compute what the superconformal blocks are in terms of the conformal blocks in any dimension between 2 and 4. So this is an important building block for everything that I'm going to say. I want to make one little caveat before going on here. Some of you may have heard there's a nice paper by Hogerforst, Ritschkoff, and Van Ries where they show that actually theories in fractional dimensions generically don't make sense. You get violations of unitarity from trace relations of operators you can build. But this usually kicks in at high dimensions for high dimension operators. And since the bootstrap tends to be relatively insensitive to high dimension operators, it turns out we don't see this, and we actually work fine. And I mean, we assume unitarity, and we work in fractional dimensions. So in principle, we should see some problem, but we don't. Presumably, if you push things further, you will. But this is just to address any issue anyone might have with this. Okay, so this is the basic setup, and now I'd like to tell you some of the nice things that come from having supersymmetry, in addition to the standard bootstrap setup. So normally, as I told you before, we impose some unitarity constraints. When you have supersymmetry, you get slightly stronger and nicer unitarity constraints. So the SUSY algebra has an R charge in it, and in terms of this R charge, you have a unitarity bound. You basically know that, for example, in the scalar sector, a scalar can either equal this particular dimension, which is a protected dimension, or if not, it has to be above some slightly higher gap above that. Thank you. So in particular, you have chiral operators, and for example, chiral scalars will saturate this bound. And so this is sort of some free information you get for the spectrum. If you know the R charge of an operator, you automatically know its dimension, and this is something we can put into the bootstrap before starting. So, you know, when we don't do the normal bootstrap, we really have very little information we can put in. Here, we already can put in a fair amount of information. And in fact, it's not so hard to imagine that you actually will know the R charge in a particular theory. So if you take very simple theories, for example, a theory with a single chiral scalar, sort of the simplest example you might think of is a theory with a cubic superpotential. And because the superpotential has to have R charge 2, you can immediately compute the R charge of the field phi from this, and it's just 2/3. So it immediately tells you that the dimension of this operator, of a theory in this operator, is d minus 1 over 3, and it's a protected operator. So if you're, well, let's put it another way. You know that there are theories which are going to have operators of this protected dimension, and you could try to look for such theories. So even if you have more complicated theories with multiple chiral fields, it's still often possible to fix their R charge using ARF maximization. In which case, again, you still have some dimensions, some data to put into the bootstrap. So we're on a much better footing than we are in a sort of normal non-conformal bootstrap. And one final point that I'd like to say that is kind of nice about this is, at least from my point of view, you know, supersymmetry, one of the problems with it is we don't know if it's going to be realized in nature, but it turns out that this small amount of supersymmetry in lower dimensions is actually suggested to be realized in nature. I'll tell you a little bit more about this. So it's believed that this amount of supersymmetry can actually be realized in the IIR of certain condensed matter systems. And that's quite nice because it means that what I'm going to tell you about actually has experimental applications. So it's kind of weird for a strings workshop, but you know. Okay, so before, I'm not going to tell you, if I have time, I'm going to say a bit more about the details of how we set up the problem, but first I'd like to tell you the results. So this is the main plot to sort of show off what we did. So this is a bound plot similar to the ones I showed you above. Here what's on the horizontal axis is the dimension of some chiral protected operator. And on the horizontal axis is with the first operator appearing, so this is phi. If we consider the phi bar OPE, there will be non-protected operators in that OPE. And this is a bound on the dimension of the first non-protected operator, which we just call phi bar. It's not really phi bar. In a free theory, it'd be phi bar. But it's just going to be called phi bar. And we found bounds for these operators, for this OPE, in any dimension between 2 and 4. And we just sort of worked in increments of 0.2. So this is the 2-dimensional bound. And this is the 4-dimensional bound. And in between, so this red line here also is the 3-dimensional bound. So, you know, it's kind of interesting. In all of these dimensions, you see there are multiple kinks that David alluded to yesterday. So that's quite interesting already. And it turns out you can do something else as well. Besides just bounding the dimension of this operator, something David also mentioned yesterday is you can study the central charge in these theories. So if you plot the central charge, you'll see, again, there's a bunch of minima, just like there was in, say, the Ising model. And in some sense, there's basically a minima corresponding to every, or minima or a maxima corresponding to every kink in this plot we had here. And there are three of them apparently in every dimension, or approximately 3 of them. Some of them disappear in various limits. In 4 dimensions, you have less. In 2 dimensions, you have less. But in between, you basically have 3 in every dimension. And if we focus on 3 dimensions, this is the plot David showed yesterday, we can explicitly see the 3 different kinks. So this is the first kink, this is the second kink, and this is the third kink, which is a bit weaker. And they lie basically at interesting dimensions. So the first one is at 2/3. The second one is at 3/4. These are sort of real fractional numbers. And this is at some number that's a little harder to determine. This is 0.86 or something. And you might have asked me before, if you were allowed to ask questions, why I have these horizontal lines here. And these horizontal lines basically correspond to d minus 1 over 3. And I'll tell you why in a second. Basically, yeah, so what I'd like to do now is focus a little bit on this first kink here and really zoom in on this region. So that's what this plot shows. It's just basically a zoom in of this region here. But I'm going to basically overlay both the bound plot for the phi bar with the central charge plot. So if you remember, this is the central charge plot. So here I'm sort of overlaying on this region in the central charge plot. And what you see is that, at least for this kink, there's a very precise matching between the minimum of the central charge and the kink in the bound plot, which is quite nice. And you see the resolution here is very high. So this is telling you there really is something interesting going on here. And I'm actually going to argue momentarily that I can make a precise and rigorous statement about what's going on here, almost rigorous statement. So the conjecture, which I think I can argue for very strongly, is that this, what that lies at this kink is simply the critical Wess-Zumino model in every dimension. And that's why what I plotted here, these dashed lines, are basically the dimensions of the protected operator, the d minus 1 over 3, in the critical Wess-Zumino model. So this critical Wess-Zumino model is just this theory I told you about. It's a theory with a single scalar and a cubic superpotential. And as I told you before, since the R charge of the superpotential is 2, you can easily see the dimension of this scalar has to be d minus 1 over 3, which in 3 dimensions is 2/3, so that's 0.66666 here. And so from my point of view, this is very nice because I didn't actually know this going into this project, but it turns out I'm just doing what I did before, but this is just the supersymmetric version of the Ising model in some sense. I mean, in the sense that the cubic superpotential leads to a quartic interaction, so if you just wrote down phi to the 4th theory and then you supersymmetrized it, you'd get, well, with 4 supercharges, you'd get this theory. So this is really the supersymmetric analog of what we did before for the Ising model. And well, at least that's what I'd like to argue. And I want to present you 2 pieces of evidence, one of them very strong, I think, that this theory really is the critical Wess-Zumino model. So the first is that it's not just a question of the dimension of the theory. When you have a cubic superpotential like this, the F-term condition imposes certain constraints. You can think of these basically as supersymmetric equations of motion. Basically, the fact that the derivative of the X term has to vanish tells you that phi squared should decouple in the theory. And you can actually see this. So thank you. So here what I'm plotting is basically the spectrum of scalar operators in the theory. So remember I told you before that actually if you're living on the boundary, as we are here, you can actually extract the entire spectrum and OP coefficients. So I can then plot them. So I plot here the spectrum of scalars appearing in the theory as a function of the dimension of the chiral field. And here I plot the OP coefficients of the associated guys. And the way to match them is just basically by the color. The red points here correspond to these red points. And the nice thing we see is that as you move towards this critical Wess-Zumino model, you had some operator at dimension phi squared, and it disappears exactly at this dimension, at this point, where you hit the dimension of the phi operator in the critical Wess-Zumino model, and you can really see its OP coefficient is going to 0 here. So this is strong evidence that you're saturating, or that you're satisfying this condition that you expect exactly at this point in the critical Wess-Zumino model. But there's even stronger evidence, and this is actually something that was pointed out after we released one of our first paper on the subject, which is that it turns out that in 3 dimensions, one can actually exactly compute the central charge of this theory, basically by computing a partition function on a squashed sphere and then taking derivatives with respect to the squashing parameter. You pull down powers of the stress tensor, and you can then compute the 2-point function of the stress tensor, and this is what I actually call the central charge. So I didn't explain this, but it's been explained in previous talks. What I mean by the central charge is the normalization of the stress tensor 2-point function. And since this squashed sphere partition function can be computed exactly, you can compute CT exactly. It's a numerical integral, but okay, that's much more exact than other things we're doing. And so it's something approximately like this, and okay, there are more terms if you keep going. But then you can compare this quantity with what we are able to compute using the bootstrap, and you see that they're consistent. And if you sort of move back up to this plot, what it means is that the exact value is sitting somewhere up here, whereas our value is down here. But that's fine because these bounds up here, the scalar bounds are going to go down, whereas these central charge bounds can only go up. These are central charge minima. But this is actually something that's much nicer than we've ever had before, at least in say, the non-supersymmetric bootstrap, because we know 2 quantities exactly. We know the dimension of phi in this theory exactly, and we know the central charge exactly. So we know this theory sits exactly at some point here in the central charge space. So if I'm able to push my numerics enough that it will go up and hit this point, my argument for the uniqueness of the boundary theory will basically tell me that I'm definitely getting the critical Wess-Zumino model, which is nice because it's no longer at the level, becomes no longer at the level of conjecture. It really becomes evidence in some sense that this is the theory we're seeing. Okay, so I am running out of time, I guess. So let me tell you a little bit quickly about what the physical applications of this. There are some. So it turns out that there's recently been some nice papers where it was conjectured that if you have a topological insulator, which is something apparently condensed matter people are very excited about, then it can realize an n equals 2 superconformal theory on its boundary. So in a topological insulator, in a 3-dimensional topological insulator, what you have is a gapped phase in the bulk. So you have some material, and the bulk of it is gapped. There's a giant mass gap, so there are no local excitations in the bulk of the material. But on the boundary, you can have fermionic edge modes living. And it turns out these fermions are relativistic, so they're actually 2 plus 1D fermions. And if you introduce some substrate above this insulator, it turns out you can sort of tune things so that there's a side of the 4 interaction of the fermions. There's a superconducting instability, and if you write down the Lagrangian for this and try to study it, a natural thing to do is to introduce a boson to rewrite this side of the 4 interaction via the Hubbard-Stratonovich mechanism. Sorry. And although this thing initially is non-dynamical, when you do RG, this generates dynamics for the bosons. So you end up for the system which has both fermions and bosons, and you can tune the mass of the bosons basically by tuning the distance of the substrate. And it turns out that in the IR, this theory becomes, although the bosons and the fermions in the original microscopic Lagrangian have different speeds of light, in the IR, these are irrelevant deformations, and they flow to a Lorentzian theory in the IR that's moreover supersymmetric. So in this paper by Ponte and Lee, they basically conjecture that there's an n equals 2 3-dimensional or 2 plus 1-dimensional theory living on the boundary of this topological insulator. And there was another paper in Science even by this group of collaborators, Grover, Sheng, and Vishwana, which basically argued, well, they focused more on n equals 1 theories, but they also argued that in this context, there are several different ways to realize n equals 2 theories on the boundaries of topological insulators. So that's kind of nice, because it means that these numbers we compute might in principle be measurable in nature. And more of our experimentalists are apparently excited about these sorts of things. Okay. So that was the first kink, which I'm focused most of my attention on because I know the most about it. The other 2 kinks are much more mysterious, and I think I'm just going to end, since I suspect my time is coming to a close, by telling you a little bit about these last 2 kinks, in the hope also that people might try to study them, because we're a little bit of a loss for what they actually are. So the second kink appears always at d over 4, and it's very clearly there between dimensions 3 and 4. It's a little less clear whether it continues to exist in dimensions less than 3. And initially, I was very skeptical about whether this kink corresponds to something physical or not. And that's simply because if you look at the constraints coming from supersymmetry, it turns out in the supersymmetric OPE, when you look at phi, not phi bar, there's some structure imposed by supersymmetry. So in this OPE, if you have phi bar, there's another protected operator phi squared, and then there can also be another protected descendant of an antichiral field, which is q squared psi bar. And these dimensions of these operators are fixed by SUSY. Okay, so I'm done. Okay, well, let me just finish with that, and people can ask me questions if they want. That's it.
Thank you very much. We have time for a couple of questions.
So, just to mention, this phi-cube theory has been studied. I mean, it's the Landau-Ginzburg CQ1, C3 alpha.
The n equals 2 minimal model. It's the n equals 2 minimal model.
Okay,
Yeah.
so
I didn't show anything there, but everything works perfectly. You go down, and even the OP coefficients, they match exactly what you expect.
Okay.
Yeah.
Can you go back to your plot showing the disappearance of the phi squared?
Could you put it? Yeah. Which plot? Sorry.
The plot showing the disappearance.
This one.
Yeah, here. Maybe this was in your paper. Did you have an interpretation of the third line, which is
This
appearing?
guy?
Yeah.
Did we have an interpretation? Not really. It's quite, well, okay, I think you may be right. This is very similar to what happened in the 3D icing, right? There's some other jump in the scalar sector. I don't think we had any clear interpretation of it, no. I don't remember, to be honest, whether, no, so it's actually not there, the critical West-Amino. I don't think we studied it. You're saying that, yeah, maybe, it might be the case that here you have a little bit more understanding of why it's disappeared from supersymmetry, so I should emphasize, what I'm plotting here are superprimaries, superconformal primaries. So this is not a descendant of this guy. So if it's disappearing, it's disappearing for some non-trivial reason. So no, I don't have an immediate interpretation. It's interesting once you definitely check. Yeah.
Okay, so that will be the last question. So please.
You mentioned that the CFT data may not determine the correlation functions of non-local observables. So what additional information you need for that?
I mean, I just say that to stave off people complaining that I'm making overly broad statements. Because it is true, for example, I don't know what additional information you might need, but if you imagine you have some gauge theory with some global part to it, I mean, the difference between SO3 and SU2 gauge theory, you're probably not going to be able to tell by a local correlation function. That's what I'm saying. If there's no local data associated with that. So I'm just making that comment. I don't know if there's any additional, one could imagine that there's some variant of modular invariance, some weaker notion of modular invariance in higher dimension that might be sensitive to things like that. Okay. I have some ideas about that, but I have nothing strong to say about it.
Because typically one builds non-local operators by smearing local operators, so it doesn't look like you would need. So at least like for Euclidean theories, which are topologically trivial.
Well, I mean, I think that you could imagine there are Wilson lines that would be sensitive to global properties of the gauge theory, which local correlation functions would not be, right?
Okay.
Sorry, can you quickly summarize why the dimension of the corresponding to the second kink is exactly d over 4?
Yeah. So basically, I mean, okay, it's an observational fact, but the argument why, just to finish this up, is basically because, so I told you there that you have this OPE here. Generically, these two fields are different dimensions, but at d equals 4, their dimensions coincide. So when the dimension of the external field is d over 4, they coincide. And moreover, this guy is a descendant of a field that's free. The dimension of psi becomes free. So it's a kinematically special point. Supersymmetry just sort of tells you the OP of this theory becomes special at this point. So you might imagine the reason we're getting this second kink at d equals 4 is simply because supersymmetry is constraining things a little. And since it's a kinematical thing, I would not, at first glance, I would feel this probably doesn't mean there has to be a theory there. It's just some interesting kinematical structure. But the fact that it doesn't continue below d equals 3, whereas the kinematics do continue below d equals 3, suggests that maybe there is some interesting theory there. It's just somehow tied to this interesting kinematics. But yeah, I have.
Let's thank Shia for this talk.
Thanks.